Hi my dear friends, welcome to complex integration. The concept of definite integral of real functions does not directly extend to the case of complex functions, since real functions are usually integrated over intervals and complex functions are integrated over curves. Surprisingly, complex integrations are not so difficult to evaluate, oftenly simpler than the evaluation of real integrations. Some real integrals which are difficult to evaluate can be evaluated easily by complex integration. In this video, I would like to illustrate a very useful and important result for complex integration, which is Cauchy's integral theorem, simply Cauchy's theorem. Cauchy, a profound French mathematician, Austin Louis Cauchy. Most of the results like Cauchy's theorem, Cauchy's integral formula for derivative, residue theorem for complex integration were contributed by Cauchy. Next, let me start what is Cauchy's theorem. See, Cauchy's theorem is, if f z is analytic within and on a simple closed curve C, then integral over C f of z dz equal to 0. You can apply this theorem only if f z is analytic within and on C. Here C is a simple closed curve. You know what's a closed curve? A closed curve which does not cross itself is called a simple closed curve, like circle, ellipse. See, this is a closed curve but not a simple closed curve because it crossed. So now you know what's a simple closed curve. Here fz must be analytic in the inside of C and also on the boundary of C. That is, fz must be analytic within and on C. So, if fz is analytic within and on C, then integral over C fz dz is 0, and this is Cauchy's theorem. So, it's very clear, if the given complex integral is suitable for applying Cauchy's theorem, then answer is always 0. That is, without any calculation, you can easily say the answer is 0. Next, consider an integral over C z by z minus 2 dz, where C is mod z equal to 3 by 2. What is C? C is mod z equal to 3 by 2. Clearly, it is a circle with a center 0 and radius 3 by 2. Next, you consider the given function and analyze its analyticity. See, here the given function is z by z minus 2. Clearly, it is not analytic at 2. So the singular point of the given function is 2. Next you check whether it lies inside or outside of the given circle. Clearly 2 is outside of C. So we can say the function z by z minus 2 is analytic within and on C. So you can apply Cauchy's theorem. By Cauchy's theorem its answer is 0. So you take fz as z by z minus 2. Clearly fz is analytic within and on C. So by Cauchy's theorem, integral over C f z dz equal to 0. That is integral over C z by z minus 2 dz equal to 0. In our syllabus, in most of the problems, C is a circle. That is, we can say 98% of the questions C is a circle. So we have to identify a circle in complex plane. So a circle is identified by its center and radius. So you consider a circle with center A and radius R in the complex plane. Then equation of the circle in complex plane is mod z minus A equal to R. So whenever you see mod z minus A equal to R, then you have to identify it is a circle with a center A and radius R. Next, watch few circles in complex plane. Consider mod z minus 1 equal to 2. Here A equal to 1 and R equal to 2. So it is a circle with the center 1 and radius 2. Next, mod z plus 1 equal to 2. Here A equal to minus 1 and R equal to 2. So it is a circle with the center minus 1 and radius 2. Next, mod z minus I equal to 1. So here A equal to I and R equal to 1. So it is a circle with the center I and radius 1. Next, consider mod z minus 2i equal to 1. Clearly A equal to 2i and R equal to 1. So it is a circle with the center 2i and radius 1. Next, consider mod z minus of 1 plus I is equal to 2. See, it is in the form mod z minus A equal to R. a is equal to 1 plus I. So the center of the circle is 1 plus I and radius is 2. So you consider a circle with the center 1 plus I and radius 2. The point 1 plus I is the ordered pair 1 1. Next consider mod z minus 1 plus I is equal to 2. Really it is not in the form mod z minus a equal to r. So you have to make it like mod z minus a equal to r. That is modulus z minus of 1 minus I equal to 2. Clearly it is a circle with the center 1 minus I and radius 2. Also the point 1 minus I is the ordered pair 1 minus 1. So clearly it is a circle with the center 1 minus 1 and radius 2. Now you are ready for identifying any circle in the complex plane. Next consider the integral over c e raised to z by z plus I into z minus 2 dz, where c is mod z minus I equal to 1. For evaluating this integral, first you identify the given curve. Here c is mod z minus I equal to 1. Clearly it is a circle with the center I and radius 1. Next consider the given function and identify its singular points. Given function is e raised to z by z plus I into z minus 2. You keep in your mind singular points are those points in which the function is not analytic. So it's very clear. Singular points are minus I and 2. For those who find difficulty for identifying the singular points, you keep in your mind those points in which denominator becomes 0 are the singular points. Singular points are those points in which the function is not analytic. So clearly minus I and 2 are the singular points of this function. Next to identify its position with respect to C. That is, you have to identify whether it lies inside or outside of C. Clearly minus I and 2 lie outside of C. Geometrically you can check, is it inside or outside? See, here it is minus I and here the point 2. Geometrically minus I and 2 are outside. There is one more way of checking whether it is inside or outside by algebraic calculation. So that calculation is, here the circle is mod z minus I equal to 1. Here you put, here we are checking whether minus I is inside or outside. You put minus I in this z. So minus I minus 2. And it is modulus of minus 2I. That is, modulus of minus 2I is square root of 0 plus 4. Modulus x plus iy is square root x square plus y square. So modulus is root 4, that is 2. Its modulus is 2. And you compare this 2 with the radius. Here the radius is 1. It is greater than 1. If it is greater than 1, that point lies outside. So clearly minus I is a point outside of C. Similarly, you can check whether 2 is inside or outside. You put z equal to 2 here, that is mod 2 minus I, that is square root of 4 plus 1. This is root 5, which is greater than 1. So 2 is also outside of C. Here, both the singular points are outside of C. So the given function is analytic within and on C. See, the function is not analytic at minus I and 2. At all other points the function is analytic. So clearly it is analytic within and on C. So you can apply Cauchy's theorem. See, Cauchy's theorem is integral over C fz dz equal to 0. Here you take fz as e raised to z by z plus I into z minus 2. By Cauchy's theorem, integral over C fz dz equal to 0. You put fz e raised to z by z plus I into z minus 2 equal to 0. Next, consider these integrals. Consider the first one, integral over C z square dz, where C is mod z plus I equal to 1. Here C is a circle with the center minus I and radius 1. The given function is z square. See, it's a polynomial, so it is analytic everywhere. That's an entire function. That means it has no singular points. So it is analytic everywhere. It has no singular point. So in particular, it is analytic within and on C. So by Cauchy's theorem, its answer is 0. So integral over C z square dz equal to 0. One thing you can notice, this integral is always 0 whatever be the curve. For any closed curve C, integral over C z square dz equal to 0 because the function has no singular points. It is analytic everywhere. Consider the second question. Integral over C sin z by z minus 2i dz, where C is mod z minus I equal to 1. Here C is a circle with a center I and radius 1. You consider the given function. It is sin z by z minus 2i. Clearly the function is not analytic at 2i. That means 2i is a singular point of the given function. Next you check whether it is inside or outside. Clearly it is outside of C. So you can say the function f z equal to sin z by z minus 2i is analytic within and on C. So you can apply Cauchy's theorem, and by Cauchy's theorem its value is 0. Next question. Integral over C sin z by z minus 1 into z plus 2 dz, where C is mod z equal to 1. Here C is the unit circle, center is 0 and radius 1. Given function is sin z by z minus 1 into z plus 2. Singularities of the given function are 1 and minus 2. Or you can easily find the singular points by solving the denominator equal to 0. By solving the denominator equal to 0, you can see the answers are 1 and minus 2. So we can say 1 and minus 2 are the singular points of the given function. That means the function is not analytic at 1 and minus 2. But both singularities are outside of C. So you can say the function sin z by z minus 1 into z minus 2 is analytic within and on C. If you take f z as sin z by z minus 1 into z minus 2, then the integral becomes integral over C f z dz. Since it is analytic within and on C, then by Cauchy's theorem you can give the answer as 0. See in these situations, see in the first situation, given function has no singular point. In these three questions, you can apply Cauchy's theorem. In the first question, function has no singular points. In the remaining two integrals, function has singular points, but all the singular points are outside of C. Here also you could apply Cauchy's theorem. So one thing we can notice that we can apply Cauchy's theorem if the function has no singular points, or if the function has singular points and all the singular points are outside of C, then also you can apply Cauchy's theorem. Next you consider this question and assume the curve C is mod z equal to 3 by 2. Suppose we wish to evaluate this integral where C is mod z equal to 3 by 2. It is a circle with a center 0 and radius 3 by 2. Here the singular points are 1 and minus 2. Clearly 1 is inside of C and minus 2 is outside of C. So here one singular point lies within C. Singular point is a point in which the function is not analytic. So the function is not analytic inside of C. You can apply Cauchy's theorem only if the function is analytic within C. Here the given function is not analytic within C. So here you cannot apply Cauchy's theorem. So in such situations, we have to depend on certain results in integration by Cauchy. Here you can apply Cauchy's integral formula. So next we have to study about Cauchy's integral formula. Integral formula is, if f z is analytic within and on a simple closed curve C and z0 is a point within C, then integral over C f z by z minus z0 dz is equal to 2 pi I f of z0. See, integral formula is used for evaluating the integral over C f z by z minus z0 dz, and it is given by 2 pi I into f of z0. See, in this integral, z0 is a point within C and f z is a function which is analytic inside of C and on the boundary of C. Let me illustrate different situations in which we can apply Cauchy's integral formula. So consider the integral over C e raised to z by z minus 2 dz, where C is the circle mod z minus 1 equal to 3. First you notice the circle. It is a circle with the center 1 and radius 3. Consider the given function e raised to z by z minus 2. Clearly 2 is a singular point of the given function. You check whether it is inside or outside of the given circle. Clearly it lies inside of C. You consider the circle with the center 1 and radius 3. Geometrically you can check whether it lies inside or outside. Algebraically you can check by taking, here put z equal to 2, mod 2 minus 1, it is 1, which is less than the radius 3. So it is inside of C. So clearly the singular point 2 lies within C. If there is a singular point which lies within C, then you cannot apply Cauchy's theorem. So you have to depend on Cauchy's integral formula. See, our Cauchy's integral formula is this one. See, in the Cauchy's integral formula, you have to select suitable Fz and Z0. Here you take Z0 as, see, in Cauchy's integral formula, Z0 is a point within C. So you take the singular point which lies within C. So you take Z0 as 2. Next we have to choose the suitable Fz. For that, you compare the given integral and the Cauchy's integral formula. So clearly Fz must be e raised to z. Okay. Then by Cauchy's integral formula, we have integral over C Fz by z minus z0 dz equal to 2 pi I into f of z0. Here Fz is e raised to z. So what is f of z0 is f of 2, because z0 is 2. Now f2 is e square. Fz is e raised to z. So f2 is e square. So 2 pi I e square, which is the value of the integral over C e raised to z by z minus 2 dz. You replace Fz and z0 here. Fz is e raised to z, z0 is 2. That's our question. So answer of the question is 2 pi I e square. Next consider integral over C sin 3z by z plus pi by 2 dz, where C is mod z equal to 5. First you notice the circle, then you analyze the singular points of the given function. Next you check the position of the singular point with respect to the circle, that is you check whether it is inside or outside. Then you apply a suitable formula for integration. If you apply Cauchy's integral formula, then you have to select suitable Z0 and Fz. Then the value of the integral is 2 pi I f of Z0. See, this is the method. So consider this question. It is a circle with a center 0 and radius 5. The given function is sin 3z by z plus pi by 2. See, its singular point is minus pi by 2. You consider minus pi by 2 as, what is pi? 3.14. So minus pi by 2 is minus 3.14 by 2. Clearly it is inside of C. So we have to apply Cauchy's integral formula. So you have to select suitable Z0 and Fz. Here you choose Z0 as minus pi by 2 and Fz is sin 3z. See, the given function has a singular point at minus pi by 2. But the function sin 3z is analytic everywhere. So in particular it is analytic within and on the given circle. So you choose Z0 as minus pi by 2 and Fz is sin 3z. Then we have integral over C Fz by z minus z0 dz is 2 pi I f of z0. It is 2 pi I f of minus pi by 2. We have Fz is sin 3z. So f of minus pi by 2 is sin 3 into minus pi by 2. We know sine minus theta is minus sine theta. So it is minus sine 3 pi by 2. Next minus sine 3 pi by 2. Sine 3 pi by 2 is, see, sine pi by 2 is 1. Sine pi is 0. Here it is sine 3 pi by 2. 1 pi by 2, 2 pi by 2, 3 pi by 2. Its value is minus 1. Sine 3 pi by 2 is minus 1. So minus 1 into minus 1, minus 1. So it is 2 pi I. If you replace Fz and Z0, you will get the question. That is integral over sine 3z by z plus pi by 2. And its answer is 2 pi I. To consider this question. See, here you have to integrate the function through 3 different circles. Consider the first circle. It is center 0 and radius 1.5. See, this function has only one singular point, which is minus 1. When you consider this circle, this singular point is inside of C. If there is a singular point within C, then you have to apply Cauchy's integral formula or integral formula for derivative. Here we studied Cauchy's integral formula, so the suitable result is by Cauchy's integral formula. See, in Cauchy's integral formula you have to choose Z0 and Fz. You choose the inside singular point as Z0 and Fz is the remaining part of this Z plus 1, that is 3Z squared plus 7Z plus 1. Then by Cauchy's integral formula, its answer is 2 pi I into f of Z0, that is 2 pi I into f of Z0, that is f of minus 1. What is f of minus 1? F of minus 1 is 3 into minus 1 square plus 7 into minus 1 plus 1. And it is minus 3. You put here, that is minus 6 pi I. So, when you evaluate this function along the first circle, you can see the answer is minus 6 pi I. Next, evaluate this along the second circle. Here the second circle is a circle with a center minus I and radius 1. Our singular point is minus 1. Clearly the singular point lies outside of C. You can check it by geometrically or algebraically. Algebraically, you take the modulus. We have to check minus 1 is inside or outside. So you put Z as minus 1. Its modulus is 1 plus 1, that is square root of 2, which is greater than the radius. So it lies outside of C. See, the given function has a singular point and fortunately it lies outside of C. That means the function has no singular point within and on C. So by Cauchy's theorem, the integral is 0. If the given function is analytic within and on the given circle, then you can apply Cauchy's theorem and its value is 0. So its answer is 0 when you evaluate along the second circle. Next, consider the third circle. See, the third circle is, it's a circle with the center 0 and radius half. Clearly minus 1 lies outside of C. Again by Cauchy's theorem, answer is 0. In these two integrals, the integrand is same, but the curve is different. First one is a circle with the center 0 and radius 3 by 2. Second one is a circle with the center 2 and radius 2. The integrand is common for both questions. Consider the given function. Its singular points are 1 and 2. See, singular points are 1 and 2. You consider the first circle, that is C mod Z equal to 3 by 2. Clearly 1 is inside of C and 2 is outside of C. See here, center is 0 and radius is 3 by 2. See, this is the point 1 and this is the point 2. Clearly 1 is inside and 2 is outside. Here you can apply Cauchy's integral formula by taking Z0 as 1 and Fz is, you choose Z0 as the inside singular point, it is 1. Next Fz. You choose see the Singular part of 1 is this 1 by z minus 1. You consider the remaining function as fz. Then fz is 2z by z minus 2. Then by Cauchy's integral formula, its answer is 2 pi I f of z naught. That is 2 pi I f of 1. But f of 1 is 2 by minus 1, that is minus 2. So answer is minus 4 pi I. See, while considering the second question, both singular points are within C. Our C is circled with the center 2 and radius 2. Singular points are 1 and 2. 2 is this point, 1 will be here. So both the singular points are within C. Since both singular points are within C, we can't directly apply Cauchy's integral formula. Here, for applying Cauchy's integral formula, first you have to give the partial fraction of 1 by z minus 1 into z minus 2. And its partial fraction is numerator is a and b. For finding a, the shortcut method is its denominator is 0 when z equal to 1. You put z equal to 1 in the left side except z minus 1. So you put z equal to 1. So 1 by 1 minus 2, that is minus 1. So a is minus 1. For writing b, its denominator is 0 when z equal to 2. So you put z equal to 2 here. So 2 by 2 minus 1. Sorry, 1 by 2 minus 1. That is 1. So b is 1. Next you multiply both sides by 2z and taking integral over c. It is let it be I1 and let this second integral be I2. That is equation number 1. Next you evaluate integrals I1 and I2 separately. See, for evaluating I1 and I2, you can easily apply Cauchy's integral formula. Next we have to evaluate the integrals I1 and I2 separately. I1 is integral over c minus 2z by z minus 1 dz. C is our circle, mod z minus 2 equal to 2. Clearly 1 is a singular point within C. So you apply Cauchy's integral formula by taking z naught equal to 1 and fz equal to minus 2z. Then I1 is this equal to 2 pi I into f of 1. That is 2 pi I into minus 2. That is minus 4 pi I. Similarly, evaluate I2. I2 is integral over c 2z by z minus 2 dz. Here c is mod z minus 2 equal to 2. Clearly 2 is the center of the circle. It is inside of c. So choose z naught as 2 and fz is 2z. Then by Cauchy's integral formula you can see this integral is 2 pi I into f of z naught. That is 2 pi I f of 2. 2 pi I f2 is 4. That is 8 pi I. Substitute these values in equation number 1. You can see the given integral is minus 4 pi I plus 8 pi I. That is 4 pi I. Next consider the integral. Integral over c 3z minus 1 by z cube minus z dz, where c is the circle, mod z equal to 1 by 3. Clearly the singular points of the function are, see, you can find the singular points by solving denominator equal to 0, which implies so z values are 0, 1, minus 1. So the singular points of the given function are 0, 1, minus 1. See, it has three singular points. Among these three, 0 is the only singular point within C. And the other two singular points are outside of C. See, here you can apply Cauchy's integral formula by taking the inside singular point as Z0 and you choose Fz as, see, this integral can be written as integral over C 3z minus 1 by z into z minus 1 into z plus 1 dz. You consider this part as Fz. See, clearly this is analytic within and on C. Clearly this function has two singular points 1 and minus 1, but both singular points lie outside of C. So we can say Fz is analytic within and on C. So you can, now you can apply Cauchy's integral formula, and by integral formula its answer is 2 pi I into f of z0. That is 2 pi I into f of 0. What is f0? f0 is minus 1 by minus 1 into 1, that is 1. So answer is 2 pi I. Summary of Cauchy's theorem and Cauchy's integral formula. Cauchy's theorem is integral over C Fz dz equal to 0. You can apply Cauchy's theorem in two situations. One is, if the given function has no singular points, you can apply Cauchy's theorem. Number two, if the given function has singular points and all the singular points lie outside of the curve, then also you can apply Cauchy's theorem. Next, Cauchy's integral formula. Integral over C Fz by z minus z0 dz equal to 2 pi I f of z0. Here, z0 is a point within C and Fz is a function which is analytic within and on C. See, this formula can be applied for evaluating those integrals which satisfies two conditions. One is, it has at least one singular point within C. And condition 2, the power of the singular part of the given function must be linear. And also notice that if more than one singular point within C, first you put into partial fraction. Then you can apply Cauchy's integral formula. By keeping these ideas in your mind, now you are ready for evaluating those integrals which can be evaluated by using Cauchy's theorem and Cauchy's integral formula. Thank you for watching.